Okay, so let us just start while waiting for Akif ya to come. Hopefully he can join us.
He already joined, but
Sorry?
he already joined.
Oh, okay. Hello Akif. Assalamualaikum. Can you hear my voice? Akif Parves. I cannot see. Oh yeah, okay. He's joining. Okay, thank you. Thanks all for coming. So, last time we discussed about we have talked about the system of particles, yeah, and how the conservation law of linear momentum and angular momentum hold in the system of particle. And what matters for the conservation laws in a system of particle is that the external force and the external torque. Yeah. So the internal forces and the internal torques don't really matter for the conservation law. So even though you have a bunch of internal forces around in your system, as long as those internal forces obey our assumptions that they are mutual and opposite, and they are along the line joining two particles between them. So those internal forces do not contribute whatsoever to the total linear momentum or total angular momentum. Yeah, if for the case of angular momentum, then the internal forces can be replaced with internal torques. So what matters is just the external force and external torque. All right, so now let's do the last conservation law, which is the energy. Yeah. Okay, maybe let's just start all over here. So remember that the work done, yeah. So I'm just going to consider all forces involved here. So the work done by all forces, all external, all forces, including external and internal, yeah. In a moving system. So you can imagine as our system of particles is moving. So if you apply forces, and also if there are internal forces applied in the system, we can define the work. Now the work, as usual, is written is denoted with a capital W. From 1 to 2, this is just integral from 1 to 2. I mean from position 1 to position 2. So I'm going to write down like this, Ri. Okay. Now, since this is the total work, okay, I should have put here the total work. Since this is about the total work, then I have to sum over I. So this is the expression for the work of one particle in a system. If I have n number of particles, then I have to sum them up. So it's like this, and this can be written. We can partition the Fi to be the external and internal. Okay, so we can write it down as two terms. The first term is the external, coming from the external forces, while the second term coming from the internal force. Now remember that the internal force is summed over J. So we have double sum here again, yeah. Sum over E and sum over J. Okay. We have integral, and then don't forget we have 1 minus delta ij times fji dot dri. Okay, so this is the expression for the total work, yeah, for the total work. Now, what can we do? Well, let me just make some diagrams like this. Maybe I'm just going to use straight line. All right, so the left-hand space, this is for this one, okay? The middle right-hand space is for this one, and the last right-hand space is for that one. All right, so now for the left-hand side, since this is a moving system, we can always write down the total force as the, oh, sorry, I forgot. As the integral of, well, this is mass times the derivative of v, of the velocity, right? Dot dri. Okay, let's work out on this left hand side first, and we know already what this is. Yeah, in the previous case, I can just do it directly. This is just d dt of we have half mi vi squared. Okay, I can as well put the summation inside, so it becomes integral of 1 to sorry, this is dt, right? So d dt of some dt. But now we know that this one, the whole integrand is just d of summation half mi vi squared. And we know that the integral of d of something is just that something evaluated between the boundaries. So now I have this, I can call it this T2 minus T1, right? T2 is just the total kinetic energy of the system at point 2 or at position 2, yeah? While T1 is defined accordingly. So now here I define T, it's just the total kinetic energy, yeah? Half okay. Right. So now if we know that vi is related to the sorry, if I scroll up here, yeah, vi is just the ri dot, yeah. So vi is just the velocity of the ith particle with respect to the origin, okay? And then we have the relation between vi and vi prime plus capital V, yeah, where vi prime is the velocity of the same particle, the ith particle, but with respect to the center of mass. And capital V is the velocity of the center of mass itself with respect to O, with respect to the origin. So now we can, okay, I think I have to extend this red line. Okay, so now we know that, as I said, Vi, this is just Vi prime plus capital V, right? So Vi squared, yeah, Vi squared, this is just Vi vector dot Vi vector. And this is just Vi prime plus capital V dot Vi prime plus capital V. Okay. Well, we know what this is, yeah. This can easily be calculated. This is just Vi prime squared plus capital V squared, right? Plus twice Vi prime dot capital V. Okay. So that means the total kinetic energy of a system can be decomposed into these terms, yeah. So T can be written as half, okay, sorry, this is summation, yeah. This is sum Mi Vi prime squared plus half sum Mi capital V squared plus the half cancels with 2, so we have sum Mi Vi prime dot V capital V. Yeah. All right. So let's leave it as it is first. Yeah. I'm going to work out on the right hand side. Now, I'm going to make another assumption here. An additional assumption is that for the forces included here, or forces involved here, all the forces are conservative. Okay, so this is my assumptions. Yeah. So all the forces are conservative. Let me just write down here. Assuming that Vi of E, sorry, this can be written as the minus grad of V. Sorry, I make a, okay, I think I was using capital V already for the velocity of the center of mass. So I'm, in order to avoid confusion, I'm going to use U of I. So this U of I is the potential energy for the ith particle. Okay. In order to avoid confusion, because we already used capital V as the velocity of the center of mass. So I don't want to use the same notation for two different concepts. Now, if you can, so this assumption is equivalent to saying that the force is conservative. So the external force here is conservative because we can always find the potential energy, yeah, related to that force, yeah, and the force can be defined as the minus gradient of the potential energy. So if that is the case, then this integral can be evaluated as follows, yeah. So this is some integral of minus, yeah, grad U I dot dri. We know already what this is. This is just minus sum of I d of U I, right? And the integral gives you, sorry, this is still under the integral, 1, 2, right? So this is just U, okay, I'm going to erase the minus, yeah. So this is just U1 minus U2, okay? Where U is the total kinetic, total potential energy at point 1, U2, so U1 is the total potential energy at point 1, U2 is the total potential energy at point 2, okay? All right, so this will contribute to the potential energy, but we also have contribution from the potential energy, the contribution for the potential energy from the internal force. Okay, so again, I will assume the same for the internal force, yeah, assuming that Fji can be written as minus delta U of Ji, right? So U of Ji is the potential energy between particle J, between the jth particle and the ith particle. Okay, so this is the potential energy between two interacting particles. Yeah. We do not specify what kind of potential energy. It can be gravitational potential energy, and that is, I think that's the most basic one, and the one that definitely exists here, since the particle has mass. So it definitely has potential, gravitational potential energy. Yeah, but it can also be other potential energy, like for example, if the particle besides having mass, it also has a charge, then this potential energy, the U of Ji, can be a Coulomb potential energy between two charged particles. So it can be any potential energy between two interacting particles. Now, what I mean by U of Ji, to be more specific, okay, I'm going to use, what can I use again? Maybe about here. U of Ji or Ij, yeah. This is a function of the distance between J and I, right? Sorry. So this is the scalar distance. Yeah. And also we know that Fji is just minus Fji is just minus, sorry, this minus Fij. Okay. So if you want to calculate this summation, yeah, this summation, well, I can write down like this. Since the summation is over I and J, yeah, so I here and J here. So I can write down, I can split dri and drj, so that, but then I have half here. So I have I, J, something like that. The same integral, this one minus delta ij, same. But then I'm putting here down. Times I have Fij dot drj plus Fji dot dri. Okay, so now I'm just splitting like this. This is just the same as twice this one. Okay, that's why I put half here. Okay, so I'm just splitting it into two, but giving half, so it doesn't change. Yeah. But then we can write down that since Fij is just the minus of Fji, okay, I can write down that this is just I'm going to combine these two summation into one symbol. Yeah. So this is sum of I and J. So the integral 1 minus delta ij, but then here I have Fij dot d of rij, where d, well, where rij is just ri minus rj, yeah, or the other way around, okay, or the other way around. Yeah, I think I have minus here. Yeah, I have minus here. All right. Then I can proceed. So what do I have here? Well, this gives us this. We already know this one, yeah. Well, since Fij can be written as the gradient of potential, so this can be written as a gradient of Uij dot the Rij, right? So this is just at the end, where after evaluating the integral, we can easily see that this is just a, we have half minus half, yeah, sum of I and j, and then 1 minus delta ij of uij. Okay. Question? Oh, okay. Sorry, I have to get something from downstairs. Yeah, so I'm going to leave for a minute. Okay.